Hi, I'm Dr. B. Ravi Kumar, Associate Professor, Department of ECE, Institute of Aeronautical Engineering. So now I'm going to discuss definitions and terminology regarding to Module 2. You know that Module 2 in Analog and Digital Electronics deals about transistor, bipolar junction transistor. Once we have studied about the semiconductor materials, how to form P and N, and then how to form PN junction diode, and the application of PN diode, one of the best application is switch, and another application is rectifier. Similarly, so we have not satisfied with that diode, so we will see that more applications when we change that pattern for that PN junction diode. So let us see that some definitions helpful to understand that fundamental knowledge on bipolar junction transistor. So basically, if you see the bipolar junction transistor is a 3-region or 3-terminal device, 3-layer device. Very simple. It is a 3 terminals. Because of 3 terminals, it is a 3-terminal device. And the first layer is called emitter, middle layer is called base, last layer is called collector. So every student might have known this 3-layer device, but you should know the area and doping of each layers. When we see this 3 different layers, doping is emitter is heavily doped. When it comes to doping, emitter is heavily doped, base is lightly doped, collector is moderately doped. When come to area, emitter is in moderate in size, base is very thin, collector is large in size. So these different kinds of different sizes and different dopings makes that device into a useful application. So the purpose of that heavily doped of emitter is basically the charge carrier. Emitter is the region which emits the charge carriers. When it is heavily doped, it emits more number of charge carriers. And base is very thin, so because it is also lightly doped. If it is lightly doped, whatever the emitted charge carriers are, just a few of them are recombined in the base and remaining all are reached to collector, so that current flow in the PN like a bipolar junction transistor. So in order to avoid that one, so we can use the lightly doped and thin region, so that every charge carriers, most of the charge carriers are reached to collector. Then question is, then if you remove base, then definitely 100% charge carriers are reached to collector. But when it is remove base region, then it is like a simple short circuit or wire. So no use of controlling of current. So base act like a base between emitter and the collector. There are 2 types of transistors, NPN and PNP transistor. Whether it is NPN or PNP, the position of the emitter, base, collector are the same. So in NPN, PNP, first layer is emitter, base, middle layer is base, and the last layer is collector. Remember that one. So I'm taking this figure to understand that the junctions which are there in the BJT and the current directions which are there in the BJT. Let us see that this diagram, in this bipolar junction diagram, provided with some bias. So with this figure, we understood that the black color strips, this black color strips, and first layer is emitter, middle layer is base, last layer is collector. The region, the junction between base, emitter and base is called emitter base junction. If you see this emitter base junction is very thin due to a forward bias connection between emitter and base. And this wider region of the junction, like a junction between base and collector, due to which reverse bias connection in the output side. So it is a 3-terminal device. So emitter, that emitter always emits the charge carriers. For example, it is a PNP transistor. PNP transistor, when we are providing forward bias at input side and reverse bias at output side, so due to forward bias, majority charge carriers are coming from emitter and reach to base, and base, due to base is very thin and lightly doped and very thin, only less number of charge carriers are recombined and The current flow in the base is very less. The remaining 90% of current reaches to collector. Of course, it is a reverse bias junction was there, and of course, it is a reverse bias biasing is applied, but it overcome that reverse bias junction and reach to collector. That's why I'm representing this. This is a big arrow to represent the majority current due to forward bias reach to collector. So I'm representing big arrow. That big arrow indicates that it will overcome the reverse bias junction and reach to collector. So that big arrow indicates that majority current, mentioning majority current. Similarly, due to reverse bias alone between base and collector, a small current flow between base and collector that can be represented by small arrow. So, my dear students, that a small black color strip and a big black color strips represented by forward bias and reverse bias junctions, and a big arrow, small arrow represented by a majority current flow due to forward bias and minority current due to reverse bias. This graph will helpful to understand that operation of the p-n junction diode. So here the current flow in the emitter is called emitter current. The current flow in the base current is called base current. The current flow in the collector terminal is called collector current. But it follows simply take that transistor as a node, and if you see that current flow in the base, current flow in the emitter IE, current flow in the collector IC, which follows this Kirchhoff current law, the total current IE is equal to the leaving current IB plus IC. So that emitter current is equal to sum of base current and the collector current. For example, 100 charge carriers are coming, 10 charge carriers are flowing, 10 charge carriers are flowing to the base, 90 charge carriers are reached to collector. The sum of 10 plus 90 is equal to 100. Likewise, it follows the Kirchhoff current law. Next, we will see that BJT configurations. Once we have known that BJT construction and operation of the BJT, then we know that there are two types of transistors, NPN and PNP transistor. If you take most of the time we prefer that symbol. It is a NPN transistor symbol. It is a PNP transistor symbol. That the head of the arrow pointing to the center base point, then it is called PNP transistor. That arrow pointing to the emitter terminal, then it is called NPN transistor. So it is called base PNP transistor, PNP. So always when both symbols, we observe that the arrow near to N. So here it is near N, PNP. Here it is near N, NPN. So BJT configurations, we have see this symbol when we would like to connect this symbol and try to understand the operation and analyze this transistor connected in a network. So in order to connecting this 3-terminal device to any network, we have some configurations. There are possibilities of ways to connect this transistor in a network. So there are based on that, we have common base configuration, common collector, common emitter configuration, common collector configuration. Let us take one example. If you take this symbol, base is connected to ground, emitter is connected to input, and collector is connected to output, then this is called common base configuration. So that the input is given between emitter to base and output measure between collector to base. And if we want to understand the behavior of transistor which are connected in either of common base or common emitter, common collector, we have to take two characteristic curves based on which we can get that what is the behavior of the BJT transistor. From the behavior we can helpful to analyze that transistor and useful to apply that analysis to the amplifier circuits. So from the definition of input characteristic, it is a graph. If you take a graph, input characteristic nothing but it is a graph between input voltage and input current by keeping output voltage constant. I am taking one graph. Let us take common base configuration. So common base configuration, input voltage is nothing but voltage between emitter and base, current flowing through the emitter, IA. Okay, and output voltage between collector and base. The current flow in the collector current is nothing but output current. So here, if you replace this input voltage, nothing but VEB and input current IE, output voltage is constant and what VCB constant. You will get graph like this. For VCB is equal to 2 volts, like that. You will get the graph. That is called input characteristics. It's a graph between input current and input voltage by keeping output voltage constant. Similarly, if you take output characteristic, it is a graph between output voltage, output current, input current is constant. What is that input current constant means in this common base configuration? Input current is emitter current and output voltage is VCB, output current is IC, and you will get a graph like this. For I is equal to some 2 milliampere. Like that, output characteristics is a graph between output voltage and output current by keeping input current is constant, so that we will understand that what is that graph, what is the behavior of that graph, from which we can get that so where which region we can which place of the graph we need to operate the transistor act as a switch or transistor act as an amplifier. And then once we know that this like a transistor connected in any network based on the configurations, then we apply the some models to understand the like analysis of that particular amplifiers. If you take any, for example, common emitter amplifier means providing any configuration and proper biasing resistors or supply voltages, and some best bias is nothing but voltage divided bias. We are providing this kind of bias and giving to some voltage and measure the output voltage. Okay, so how to analyze whether it is good or bad? We can analyze by taking a model, nothing but H parameter model. By taking the H parameter model, then we will find out that 4 important factors: current gain, input resistance, voltage gain, and output resistance. So that what is the, after deriving the equations, current gain is equal to minus HFE by 1 plus HY into RL. What does it mean? Means HFE nothing but current gain in of a transistor H parameter, and output like 1 plus HY into RL, output admittance into RL. So this is nothing but current gain formula. So these 4 formulas are helpful to analyze that particular amplifier. So input impedance is nothing but HIE plus HRE AI into RL. Once we found AI just before, then we substitute then the RI, we will get the RI. And then once we find AI and RI, just AV is equal to AI into RL by RI. And output admittance or output resistance we can find from this equation. So that once we know that current gain and the resistor and the voltage gain and output resistance is helpful to analyze the amplifier, like a common base, common emitter, common collector. Based on this only, we always prefer that common emitter amplifier used as an amplifier. Common collector act as a buffer, like at output stage. Common base always at input stage. This conclusion, this inference drawn from that analysis of an amplifier with the help of modeling, H parameter model. So these are the important concepts or terminologies and definitions. You have seen these definitions from the IARE website of AD subject, and then we have also studied from this electronic device and circuit, RSA, or Shalivahana, Millmans, all those things we have studied. So go through that one. And this is all about definitions and terminologies from the module 2. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.